The best way to analyze a simultaneous game with two players is to construct a table. Use the rows to show the strategies available to one player and the columns to show the strategies available to the other player. Use the cells to show the payoff to the players for each combination of strategies. Before proceeding, pause this video and watch clip 1 in the questions for discussion, question 2. Clip right there. I will use it as an example and show you how to identify Nash equilibriums. So I'm going to pause, you pause it, and then come back when you're ready. Okay, to illustrate this game, I will construct a 4x4 table. I'm going to enter a table right here. Table, insert table 1, 2, 3, 4. 1, 2. I'll put a 4x4 table in, and I'm going to use the one row to show the first player. I'll use woman as the what we'll call the column player. I'll use man as the row player. Woman has two strategies. She can split. She can steal. Man has two strategies. He can split. And he can steal. So I use two of the columns to show the strategies available to the woman and the two rows to show the strategies available to the man. Inside of the cells, I'm going to enter the payoffs to each of the players for that combination of strategies. If they both choose split, they both get $50,000 and $75. Now, by convention, the first payoff is the payoff to the row player, and the second payoff is the payoff to the column player. So this first number, $50,075, is what the man's going to get. $50,075 is what the woman's going to get. If the man splits and the woman steals, the man gets 0, and the woman gets $100,150. If the woman splits, the man steals, man gets 150, 100, 150, and the woman gets 0. If they both steal, they both get 0. To identify Nash equilibriums, I highlight the highest payoff for the column player for each row and the highest payoff for the row player for each column. Any cell that has both payoffs highlighted indicates a Nash equilibrium. So if woman chooses split, the man will either get $50,075 or $100,150. $100,150 is higher, so we'll highlight that with a nice yellow. If the woman steals, man is going to get 0, 0. Man doesn't care, so we'll highlight that with yellow and that with yellow. When you get a tie, you just highlight all of them. If the man splits, the woman will either get $50,075 or $100,150. $100,150 is higher, so we're going to highlight that payoff for the woman. If the man splits, the woman has a higher payoff as she steals. If the man steals, the woman's indifferent between splitting or stealing. She gets 0 in either case. So we'll highlight both of those. And that was a little bit better. Let's go on and change the color here a little bit. Oh, yeah, let's change the color for the woman. Instead of being yellow, let's make it be, we'll make it be green. That'll work for me. I can fix that real fast. That one's there, and we got one more to do. That'll be there. There we go. So, the yellow shows the highest payoffs for the man, given what the woman might do, and the green shows the highest payoffs to the woman, given what the man may do. Any cell with both payoffs highlighted is a Nash equilibrium. Well, looky here. We have 3 Nash equilibria. Split, steal, 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 and steal, split. All 3 of these equilibrium are weak, at least one player is indifferent to its action and the alternative. For example, if the woman steals, the man doesn't care whether he steals or whether he splits because he gets 0 in both cases. However, split steal and steal split are Pareto efficient relative to steal steal. One player receives a higher payoff than one player gets a higher payoff in the two Pareto efficient equilibria than they do in steal steal. For example, the man would receive a higher payoff for example, if we go from steal steal to split steal, the woman's payoff increases and the man's payoff doesn't change at all. So split steal is Pareto efficient relative to steal steal. Note, split split is not a Nash equilibrium. For example, the man would receive a higher payoff by unilaterally choosing steal instead. His payoff would go from 50,075 to 100,150 if the woman's choice remains constant. Of course, if both parties change their positions, both would be worse off. They'd wind up at the 0-0 outcome. Predicting an outcome in this game is difficult. Normally, I would use a Pareto efficient outcome to form a prediction. However, here we have two Pareto efficient outcomes, and they are diametrical opposites. Using game theory to make a prediction also requires that the payoff reflect accurately what the players value. In this game, the monetary payoff may not capture everything that matters. Fairness, empathy, social norms, and history may influence the split steal decisions in addition to the monetary payoff.